Evgeny Mozgunov, and today I'm going to talk about the theoretical solution to the problem of effective Hamiltonian and its application to experiments in quantum simulation. I will first present what effective Hamiltonian is and how do I find it, and then I will review the field of quantum simulators and explain how my result applies to this field. And finally, I will present another more technical result about the specific statements appearing in the first part. The take-home message of this talk is that both cold atoms and superconducting qubits can be proven theoretically to work as quantum simulators. Effective Hamiltonian is a problem that can be stated as follows. If we're given a Hilbert space H, a wave function psi that is evolving in time according to the Schrödinger equation with the generator H, the Hamiltonian, we want to find an effective wave function in an effective Hilbert space, where evolution is generated by an effective Hamiltonian, together with an isometry between the original Hilbert space and the effective Hilbert space. And this effective Hamiltonian has to satisfy the condition that the evolutions are close. In practice, people talk about effective Hamiltonian most commonly in the following two cases. First is what I call Born-Oppenheimer, which is when we want to restrict our dynamics to a low energy subspace. And the second is the rotating wave approximation, where the effective Hilbert space is the same as the original Hilbert space, but the Hamiltonian changes. We want to get rid of the fast rotating terms. These two methods, rotating wave approximation and Born-Oppenheimer, solve the problem of effective Hamiltonian in the case where this effective Hamiltonian is time independent. And these solutions have been known for many years. However, if the effective Hamiltonian that we want to get is time dependent, there wasn't an immediately available solution in the literature that stated if there are any extra terms that appear. So we, in this work, show that there was actually a result in the literature that was well known for a long time that solves this problem. And that result is the adiabatic theorem. In fact, the statement of the adiabatic theorem is that there is some effective evolution that stays in a low energy subspace. And this effective evolution is exactly what we wanted in our effective Hamiltonian problem. Now we're going to define what are those quantities. First of all, we will change time to an adiabatic parameter, which divides the time by the total evolution time. The Schrödinger equation then looks like this. Formally, for adiabatic theorem to work, the low energy subspace that is here denoted by P, the projector on it, has to be separated by a gap in the spectrum of the Hamiltonian for all values of the adiabatic parameter S. We call this gap M here, which is a somewhat unusual notation to specifically emphasize that this is not a gap between the ground state and the first excited state. It's the gap between low energy subspace and the high energy subspace. Now, adiabatic theorem tells us to formulate the following approximate equation. And that approximate equation will generate an evolution that in fact stays in the low energy subspace. For every projector P, there is in fact an isometry that maps the Hilbert space into a smaller Hilbert space of dimension p, and there's a freedom how to choose the basis in that smaller Hilbert space. So we fix that freedom at the beginning of the evolution by choosing the isometry v0. But at other points in the evolution, we actually have to be more specific, so we can't just choose any v. In fact, in principle, we could choose arbitrary time-dependent basis, but there is a preferred way to do so. So the preferred way is given by the unitary U effective, and the time evolution of this unitary is given by this equation. And U effective evolves the original isometry in such a way that there is a small dimension vector, psi effective, which is exactly what we wanted in our problem of finding effective Hamiltonian, whose evolution is given by the Schrödinger equation with the effective Hamiltonian. Effective Hamiltonian is just the isometry of the original Hamiltonian. Using these definitions in the statement of the adiabatic theorem, we exactly get the statement of the problem of the effective Hamiltonian. Why did we choose the basis this way? Is as follows. Observables in this basis also change adiabatically with time. There is no fast time dependence in those observables. In previous methods, people guessed that this is the desired property, and they fixed the basis by choosing some observable to be exactly constant. For example, they chose persistent current in flux qubits. The problem with that choice is that it will give slightly different bases, and strictly speaking, the H effective in that basis will have geometric terms, which is very counterintuitive from the experimental point of view, because then H effective will have a deformed spectrum that doesn't exactly match the original spectrum. And if we throw away those geometric terms, then the error of the evolution may actually be big, even in the adiabatic limit, because this bound doesn't apply. So now that the statement of our result has been made, we want to describe how does it apply to the field of quantum simulators. All the work in the field, from which I here draw 5 exemplary references, can be put into one of these categories. There are works on superconducting qubits and cold atoms, well, technically also ions. There are works that do ground state preparation or genuinely simulate non-equilibrium dynamics. And there are works that use a digital approach to quantum simulation or analog approach to quantum simulation. If they do use analog approach to quantum simulation, they probably use some approximations to implement the effective Hamiltonian, from which the first 2 we already described. And the third one is coupling via waveguide, which is a little bit more complicated than the other 2. Our method that we presented just now applies to both superconducting qubits and cold atoms. It is meaningful to use it in the context of ground state preparation and simulating dynamics, and of course it is about the analog. So I would like to note that it is not clear at this point whether the analog approach to quantum simulation is better than digital or not. I would like to mention that the other 2 approximations that are commonly used in the analog approach can be, in fact, described by our previous paper and the general techniques that apply there. But that's not the purpose of this talk. So if we are in the context of ground state preparation, technically our result is not necessary for doing the experiment and doing research in that area, because all we need for ground state preparation is to make sure that the final Hamiltonian, when we want the desired ground state, is the one that we need. However, if we do have our result that describes how the Hamiltonian got there, it's much easier to present the ground state preparation algorithm, which is usually some kind of adiabatic algorithm like this. It is also more compatible with existing theoretical proofs that are for Hamiltonians like this. And finally, experimentalists will have an easier time to calibrate their device. If we are in the context of dynamics, then the only way to make quantitative statement about quantum simulation of non-equilibrium dynamics is to use some kind of a result like ours. So now I would like to briefly state the more technical second result. So the thing is that the effective Hamiltonian or adiabatic theorem would have to be accurate to some error, and that error has been precisely presented by the adiabatic theorem stated in the paper by Janssen. However, their bound is only valid for Hamiltonians which derivative with respect to the adiabatic parameter is bounded. So the bound diverges if this derivative is if the bound is this h prime is infinity. And however, in practice, many Hamiltonians that we deal with do have an unbounded derivative. In particular, the Hamiltonian of a flux qubit has this mutual inductance terms, and the derivative of those have unbounded norm. Here we control the barriers, the phases, and the mutual inductance terms. Now, instead of the norm of the Hamiltonian's derivative, we use the following quantities. We use the ratio of the derivative mutual inductance matrix to the smallest eigenvalue of it. We use the energy scale formed by some of these derivatives. And we also will need an adiabatic time scale that is formed by the gap of the Hamiltonian, and it's possibly either dimension or the norm of the low energy subspace Hamiltonian. Now, after we define those time scales, we finally can state the adiabatic theorem, which is the difference between the low energy subspace evolution and the true evolution. The difference between evolution generated by effective Hamiltonian and true evolution. And this is this big formula that I'm just gonna leave on the slide, and I'm happy to receive any questions. I would like to note that the right-hand side is finite, even though the derivatives diverge in our example, and our result is generalizable to many almost all physically realistic examples. Thanks for your attention.